energy of the diatomic molecule and internuclear distance between the two atoms. So if on y-axis is the potential energy and on x-axis there is the internuclear distance, then potential energy curve can be drawn as curve between potential energy of the system and internuclear distance between the two atoms. And it has been found that potential energy of a diatomic molecule first decreases with the decrease in internuclear distance, becomes minimum at a point called the equilibrium internuclear distance, that is E, and if internuclear distance is further decreased, then it increases abruptly, because at first when internuclear distance is decreased, the energy of the system decreases due to the increase in stability, because a stable bond is formed, and when this internuclear distance is further decreased, there will be the repulsions between the two atoms, and which will increase the energy of the system, and hence this potential energy increases abruptly. So this is the potential energy curve. It is also known as the Morse potential energy curve. Now this potential energy curve is further divided into vibrational energy levels, and which are known as V0, V1, V2, V3, V4, V5 and so on. These vibrational energy levels are further divided into rotational energy levels, which are not shown over here. So any transition that will occur from V0, that is lowest vibrational ground energy level, to the higher vibrational energy level, will be accompanied by the rotational transition. And in a diatomic molecule system, there are so many these potential energy curve for each electronic state. This is the potential energy state for the ground state, and a similar potential energy curve will be there for the first excited state, which will be similar, but the difference will be only that the equilibrium internuclear distance will be at the higher internuclear distance as compared to the ground state. So this equilibrium internuclear distance RE, and this is the equilibrium internuclear distance for the excited state RE dash. It is at higher internuclear distance, and the dissociation energy D2 is lower than the D1. Dissociation energy D2 is lower than the D1 because in the excited state the bonding between the two atoms is weaker as compared to the ground state. Now what is the dissociation energy? For example, if a electron is placed over here and if it absorbs energy, then it can go from V0 to V2, V3, V4, V5 and so on. But if energy is sufficiently high to excite the electron from V0 to here, then the electron, now there is no bonding between the two atoms because bonding was up to here only. So the two atoms will dissociate. The molecule will dissociate into the atoms, and this is known as the dissociation energy. This much amount of energy is required to dissociate a molecule into the atoms, but usually this does not happen, because if this happens, the molecule absorbs energy and get excited to the higher exciters, and hence this is the potential energy diagram for the diatomic molecule.